So uh, this presentation is about a paper that I put out in 2019 on how we can make differentials act more algebraic, and we'll uh, we'll deal with this. I'll introduce the question as we go along, but many people have asked about this paper, and so this is kind of an explanation of that paper. It doesn't require that you have a deep understanding of calculus, or actually, we'll actually introduce calculus, so you might be able to get away with not having any knowledge of calculus in order to follow it. Um, but anyway, so for those who are interested in what the paper said and why things were said the way they were said, this video will hopefully explain why. So let's start with a little bit of background. Calculus and infinitesimals. All right. So first of all, what is calculus? So calculus is basically the study of how you gain knowledge of mathematical objects by slicing them up into infinitely small pieces. Before calculus, there were some specialized ways of doing this. Archimedes did a lot of this sort of thing, but everything that he did was kind of specialty. Special formulas, special ideas, and calculus really took the idea of slicing things up into infinitely small pieces and made it a very rigorous and workable system. Um, and it turns out that when you slice things up in infinitely small pieces, they actually become easier to deal with. It's easier to deal with the infinitely small pieces of a mathematical object, a formula, a geometry, something like that, than it is to deal with the bigger object. And so by slicing it up into little tiny pieces, you can oftentimes simplify your life. So there's two main tools of calculus. There's the derivative, which is related to slope, and the integral, which is related to the area under a curve. All right. So for example, if you have the equation y equals x squared, calculus will tell you that the slope, which is the derivative, at any point of this equation is 2x. So if you think about, so you've got y equals x squared. If you go along along the x-axis, at x equals 3, the y value will be 9, but the slope at that point will be 6 because the derivative, which is the slope, is 2x. Now how you determine that we'll get into a little bit later. But that's what the derivative is. It's an equation that tells you the slope at any given point. The area under the curve at any point is given by x cubed over 3. So if I go along the x-axis and I find if I go over 3 on the x-axis, then the y-coordinate is going to be 9, and it turns out so is the area, because 3 cubed is 27, divided by 3 is 9. So so that equation tells you if I'm going to bound, take the area between the x-axis and the top of the curve and the y-axis, that will tell me what the area under the curve is for any point along that curve. So anyway, those are the two major tools. Again, we're not going to go into right now how those are determined, but that's kind of the idea behind them. So calculus is what teaches us how to perform these operations. So since slope is such an important part of calculus, let's talk about what slope is. Okay. So for a line, the slope is the ratio between how much a line goes up compared to how much it goes across. We also call this rise over run. And you can calculate this on a line by taking any 2 points and dividing the change in y by the change in x. So if I've got a line, I can take any 2 points, so we'll call those x0, y0 is the first point, and x1, y1 is the second point. And the slope between them is simply the difference of the y values divided by the difference of the x values. However, it gets different on a curve. On a curve, the slope continually changes, and therefore it's a function of where it is on the graph. All right, so if I take a look at the slope, we can see that this curve, this is y equals x squared, this curve has different slopes depending on where you are. So on the left side, you can see that yellow line, that slope intersects at about x equals negative 0.5. And so you can see that it's sloping down. But you can see at the very bottom of the graph, that slope is flat. So that green line shows you the flat slope at the bottom at x equals 0. And then at the right, you can see that the red line shows us that it's sloping upwards. So at each different point on the graph, you have different slopes. So you can't just say, oh, well, we'll just pick any 2 points, because at every point, the slope is actually going to be different. All right, so since at every point the slope is different, it's harder to find slopes on a curve than it is on a line. Now, we can estimate it by picking 2 points which are really close together. But again, if I pick 2 points that are really close together, that's still just an estimate. If I want to know what the slope is exactly, I'll need some more complicated tools. In fact, so what we can do, remember I said calculus is about slicing things up into infinitely small pieces. So what I can do is I can find 2 points that are not just close together, but they are infinitely close together. Okay? So in other words, the difference between the 2 points is infinitely small. And we call infinitely small values infinitesimals. All right? And so since these are infinitely small differences, we call these infinitely small differences differentials. Okay? So let's look at this graphically. So again, on a line, we could pick any 2 points we want, and they'll all give me the same slope. Okay? However, if I go to a graph, just any 2 points won't do. Now, I could pick 2 points that are really close together, right? So if you look on the right, you can see these 2 points that are not really close together, and the slope between them, it's kind of a okay-ish approximation of the slope, but it's actually really pretty far off for either point. On the left-hand side, though, you've got 2 points that are pretty close together, and so the line between them pretty much accurately represents the slope, but again, it's not exact. It's a reasonably accurate slope, not the actual slope. So to get a result that has infinite amounts of accuracy, we need 2 points that are infinitely close together. So how do we generate these points that are infinitely close together? All right, so in calculus, we need to develop some notation to talk about points that are infinitely close together. All right, so if we have a variable y, then an infinitesimal change in y, that's an infinitely small change, is denoted as dy, which is the differential of y. Remember, an infinitely small difference is a differential. So dy is the differential of y, or an infinitely small change in y. So the infinitesimal change is a differential, and remember, so the thing to keep in mind is that dy is a single unit. It's all together. Don't think of it as d times y. It is not d times y. It is dy. It's its own thing. You can think of it, if you need to, as d of y, like it's a function, like a differential of y. Like you'd have sine x, cosine x, sine y, cosine y. We can have dy. So what's inside is actually being evaluated by, it's actually not a function, it's an operator. But nonetheless, that's the way that you can think of it. So, the slope of a curve at any point can be thought of as a ratio between infinitely small changes of y, called dy, at that point, compared to the infinitely small changes in x, called dx. Now remember I said earlier that the slope of x squared at any point is 2x. So we can express this as by saying dy over dx equals 2x. Now, of course, I still haven't told you how you figure that out, but I'm just introducing some notation so you'll be more familiar with how this works. All right, and so again, graphically, y equals x squared, and dy over dx equals 2x, and you can see at x equals 0.5, if I draw a line that matches the slope at that point, the slope of that line is 1. Okay. So how do we do calculus? And is it hard or is it easy? Well, it turns out that calculus, doing differential calculus, where we come up with derivatives, is actually pretty straightforward. So how do we know that the derivative of y equals x squared is dy over dx equals 2x? All right, well, there's actually just a simple set of steps to do this. And this set of steps is the same for every problem. It turns out calculus has some rules that make it easier for some more complicated problems, but you actually don't need all of the calculus rules. You can just do this handful of rules and get the right answer. The other rules simplify things. They kind of include some tricks that you might have to do yourself, but you can actually get away with just these rules. All right, so we're going to take the original equation, and what we're going to do is we're going to replace every occurrence of y with y plus dy. And we're going to replace every occurrence of x with x plus dx. All right, so we're basically saying what value of this infinitely small change in y and infinitely small change in x would cause the equation to still be true. All right, so then once we do that, we're going to solve for this ratio, dy over dx. And once we do that, we're then going to go back and we're going to eliminate any terms that have differentials that aren't in ratio with other differentials. And the reason for this is simple, is that a differential is an infinitely small value. So if we just got infinitely small values hanging on, they are effectively zero. Now if you put differentials in ratio with each other, then their amount of infinitely smallness kind of cancels out and you get an actual value. But if you leave differentials alone, they actually get so small that they can be effectively rendered as zero. Now there's more technical ways we can treat this, but that's good enough for what we're doing right now. So let's do this process. We'll start out with y equals x squared. Now remember, we're going to replace every occurrence of y with y plus dy, and every occurrence of x with x plus dx. And that gives us the following formula. Now remember, when we replace these things, we put them in parentheses so that our order of operations is maintained. So here we go. Y plus dy equals the quantity x plus dx squared. All right, so what we're going to do is we're just going to multiply through that right-hand side, and that gives us this equation. All right, so this is just what happens if you square that x plus dx. Now what we're going to do is we're going to subtract. So we're trying to get dy over dx by itself. All right, so on the left-hand side, we have y plus dy, so we're just going to subtract y from both sides. All right, so that's a pretty straightforward operation. I put it in kind of a funny place, though. I put the subtraction right next to the x squared, and the reason for that is because if you look in the first equation, we see that y is equal to x squared. So x squared minus y is actually 0. So we can actually get rid of both those terms. So now we have dy equals 2x dx plus dx squared. All right, and then we're trying to solve for dy over dx. So all we have to do now is divide both sides by dx. And that gives us dy over dx equals 2x plus dx. Now remember, differential by itself is effectively 0. So that means that's essentially 2x plus 0, so dy over dx is 2x. And so that's how you find out, given an original equation, what the equation for the slope is. All right, so that's doing calculus with infinitesimals. However, when they first introduced infinitesimals, there were quite a few criticisms. Now, early calculus, it focused heavily on infinitesimals, especially Leibniz. There were two main people who generated calculus. One was Leibniz, the other one was Newton. Leibniz's was very explicitly dealing with infinitesimals. So as I mentioned, the differentials dx and dy, they're thought of as infinitely small values. And in some cases they're acting like 0, and in other cases they're not. As I mentioned earlier, when you put them in ratio with each other, they act as regular values, but when they're on their own, they kind of act like 0. Now, in Leibniz's time, a formal theory of differentials had not yet been built. And so therefore this kind of gooey mess of sometimes they act like values and sometimes they act like they're 0, that drew a lot of criticisms. And so there wasn't a formal theory to say when we should do one, when we should do the other. And so this led to some some problems, and this was epitomized by the criticism of George Berkeley. And he kind of gave it to the mathematicians. He said, now this uses some old terminology. So when you hear fluxions and evanescent increments, these are just words that represent differentials and infinitely small values. He says, and what are these fluxions? Are they the velocities of evanescent increments? And what are these same evanescent increments? They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? So basically the fact that you can treat this as both zero and not zero, depending on the context, it's like, wait, it's not nothing, but it's not something. It's like a ghost of a departed quantity. But, that raised a lot of ire, and that's a pretty quoted mathematical statement that's been kind of given play over the years. But I think his next statement was what really got people's ire. He says he's relating mathematics to theology, and he says, and basically this whole book is he addressed it to what he called the infidel mathematician, and saying, and mathematicians always thought of themselves as being higher than theology, and that what mathematicians were doing was rigorous, but theology requires this idea, all these mystical notions, and so math was solid and theology was flimsy. And so what Berkeley comes and says is, he says, he who can digest a second or third fluxion, a second or third difference, need not, methink, be squeamish about any point in divinity. With what appearance of reason shall any man presume to say that mysteries may not be objects of faith, at the same time he himself admits such obscure mysteries to be the object of science? So he's saying, if you can, because, we've just talked about differentials here, but you actually, in calculus, you have second differentials, which is infinitely smaller than an infinitely small value. You have third differentials, which are an infinitely small relative to infinitely small relative to infinitely small. And he's like, if you can digest a second or a third infinitesimal, why are you being squeamish about theology? He's like, the objects in math are no less mystical than what we're dealing with in theology. And so this comparison of mathematics to theology was not taken well, and so the race was on to base calculus on something other than infinitesimals. And so this led to doing calculus using limits. All right, so they reformulated calculus so that you didn't have to use infinitesimals, and instead used a technique known as limits. The problem is that while infinitesimals are very, very clean, as I showed you how to do differential calculus in like 5 minutes. They're very clean and easy to use. Limits are much more cumbersome. So this made calculus a lot more complicated, but it also meant that you could do away with infinitesimals and the associated theological baggage. So now the thing is, they kept the notation. All right, so the notation of dy over dx representing the derivative, that stayed. But the rules of calculus using limits now stipulated that these quantities were meaningless when separated from each other. Okay, so dy didn't mean anything on its own. Dx didn't mean anything on its own. They only meant something when in ratio with each other. So this ratio was stuck together, but never to be separated. Now, people did successfully use these quantities separate from each other, but it's generally considered an abuse of notation. All right, so yeah, you can get away with it, but you really shouldn't. All right. So this leads to a problem. This works fine in the first derivative. Some people abuse notation and some people get away with it, but there actually is a problem when you get to the second derivative, which is the derivative of a derivative. Right. So the derivative of a derivative is known as the second derivative. So so y equals x squared, the derivative dy over dx was 2x. Well, that's itself is an equation that you can take the derivative of, right? So the standard form of this notation is this, all right? And it's this. The way that you read this is the second differential of y over the first differential of x squared. All right, so that's the differential So you can, if you were to write this out more fully, you would say it's the differential of y over the differential of x times the differential of x, right? So the problem is that in this form, if you separate out the differentials, it's not just an abusive notation. You actually get values wrong. Okay. Now, this isn't a problem per se, because there is a rule for doing some of these types of manipulations, and it's known as the chain rule of the second derivative. But the problem is that it doesn't match the algebra of the notation, right? So it basically you have to keep the derivatives in the differentials in ratio with each other. You cannot treat them as if they're separate. Okay, so let me show you an example of how this goes right and goes wrong. All right, so let's say we have a system of equations, y equals x cubed, and that same x is equal to t squared. All right, so if I take the derivative of these two equations, I can say dy over dx equals 3x squared, and dx over dt equals 2t. And you can figure this out using the same process that we did earlier. All right. Now, in the first derivative, we can treat the differentials algebraically. So, for example, let's say we want to solve for dy over dt. All right. Well, you can see algebraically that if we multiply dy over dx times dx over dt, we'll get dy over dt, because the dx's will cancel. So that means if we multiply the left sides and we get the right answer, since the left sides and the right sides are equal, we can multiply the right sides by each other and get the same thing. And indeed, we will get 6t to the fifth. And this is exactly the same value you'd get if you substituted x equals t squared into the first equation and just did it like normal. Okay. The problem comes in the second derivative. All right. So here's the formulas, and this is both the first derivative and the second derivative formulas. Okay. So the problem is that if you could actually separate out the differentials here, then if we wanted to solve for the second derivative of y with respect to t, then we should be able to just multiply it by dx over dt squared, right? Because that would cancel out our dx's and leave the second differential of y over dt squared, right? But this actually leads to the wrong answer. If you do this, you get 24t to the fourth. But the answer should be 30t to the fourth, which you would get if you substituted x equals t squared into the first equation. All right, so why do you get this discrepancy? Well, here's the standard view. The standard view says that the chain rule gives you the right answer, but this means that you can't treat differentials as algebraically manipulable units. That the reason that you're getting the wrong answer is that you can't the second differential of y over the differential of x squared is not actually a ratio, and therefore you shouldn't expect to be able to treat it as one. And it views this as non-problematic because the current standard view that uses limits instead of infinitesimals, they think that infinitesimals and differentials are meaningless anyway, and therefore you shouldn't ever manipulate them algebraically. It's just wrong to do that. We show them in a ratio just for historical purposes, for historical reference. There's no real meaning to the ratio, and so that's the standard view. And so we use a separate rule called the chain rule for the second derivative, because the notation it isn't actually a ratio. The ratio is just in your mind. So, and since they're infinitesimals, we shouldn't expect there to be a valid ratio anyway, right? Because we don't expect infinitesimals to work because that's old stuff. Limits are the new thing. So, how do we fix this issue, right? As if you might have guessed, I'm in favor of infinitesimals. In fact, in the 1960s, we had a rebirth of infinitesimals because a mathematician by the name of Abraham Robinson was able to form a rigorous formulation of infinitesimals, and he created what's called the hyperreal number system, which includes both infinities and infinitesimals. So, because of his work, we now have a rigorous way of including infinitesimals. So this brought back in the use of infinitesimals back into calculus, and they call this non-standard analysis. And so this gave us a justification for treating differentials algebraically. The problem is that most treatments using non-standard analysis only talked about derivatives in the first derivative, and generally left out higher order derivatives and differentials, or left them unexamined, or sometimes they just repeated the old way and didn't talk about the fact that there was a problem. So why was there a problem? Well, it turned out that the defenders of differentials and infinitesimals actually didn't take their own theory seriously enough, right? Because the formula, the second differential of y over the differential of x squared, doesn't take into account the actual order of operations of the second derivative. What the formula implies is that you take the differential of y twice and then divide it by the square of the differential of x. However, the second derivative is actually the differential of the derivative divided by the differential of x. And you could write this like this. So it's the differential of dy over dx, not the differential of the differential of y, it's the differential of the ratio of the differential of y over the differential of x all over the differential of x. And so calculus actually has a rule for dealing with quotients, and it's just that nobody took dy over dx seriously enough as a quotient to use the quotient rule. And it turns out that if you use the quotient rule for taking the differential of dy over dx, this actually becomes the formula that you see on the bottom left hand of the screen. So that's the second differential of y over the differential of x squared minus the differential of y over the differential of x times the second differential of x over the differential of x squared. And that's what the notation of the second derivative should actually be. So this actually is a valid formulation of the second derivative in which you can treat differentials algebraically. All right. So the advantages of this is using the new notation, differentials can be fully algebraically manipulated using standard algebra rules in all cases. All right. So we can multiply both sides by dx, it still works. Divide both sides by dq, it still works. You can treat them all just using standard algebra rules. Things will cancel, things will multiply, it all works out great. The notation also has a clear reason for being the way that it is. The previous notation, I read 10 different calculus books trying to get an explanation for the other notation, and none of them bothered to even try to give you a reason for it. This notation has a clear reason for being what it is. It is the application of the quotient rule to the quotient dy over dx. All right. So now we also got rid of separate memorized rules for doing manipulations. You don't need the chain rule for the second derivative because you could just manipulate it algebraically to get what you want. I mean, you can use the chain rule. You know, if you have that rule memorized, that will help you remember which operations you should do. But you don't actually need the rule because you can literally just manipulate it algebraically. There's actually another rule as well. So not only do you have the chain rule for the second derivative, there's also an inverse function formula. So you can take the second differential with respect to, or basically the second derivative of y with respect to x, and change it into the second derivative of x with respect to y using the inverse function formula, which you can derive entirely through algebraic manipulations. In fact, you can even, using this new formula, what I'm most excited about, although I haven't had the time to do deep a deep dive to figure out how this could be applied. But in the new formulation, we can generate new ratios, such as the second differential of y over the second differential of x. This actually is a ratio that's not expressible using current standard notation. Why? Because you can't uh, cancel out differentials in higher order derivatives using the standard notation. So, and then finally, this gives a clearer picture for what is actually happening in higher derivatives in terms of first order changes. I'm also told, I haven't looked into this a lot myself, but I have heard that in software-based automatic differentiation, which they use in some machine learning situations, that this actually matches what people are already doing in machine learning. So now the formula for the second derivative matches what people have found out that they have to do in automated differentiation. So some general notes. So people avoided infinitesimals and differentials, and they greatly complexify their subject to avoid religious implications. And I've seen that happen in more than one field, but I find it interesting that it occurs even in math. And so these complications led to inconsistencies. And after a while, the practitioners started to just take these inconsistencies for granted. They're like, oh, well, this notation, it isn't real, so we shouldn't expect too much of it. And so they started, they basically, I think no one bothered to look for, I mean, as you saw, the fix is very simple. It's simply treat dy over dx as a quotient when you take its derivative. That seems very straightforward, but no one bothered to because they just took it for granted that it shouldn't work. And then, when the infinitesimals were reintroduced, practitioners failed to revise the notation simply because they'd taken it for granted for so long. And so I find that really interesting that sometimes people get stuck in a habit of mind of doing something that even when they get a solution, they don't even know to apply it. And I think this has a lot of applications in a lot of places. Another thing that I find interesting is the hyperreal number system is actually largely unexplored. A lot of people, there's been some people who have used it to good effect, but on the whole, people have not sat around and thought, how can the hyperreal number system make my area of inquiry easier? I think it actually will, because we've the hyperreals, some things that it's shown us already. First of all, by taking the hyperreal seriously, we can actually extend this to partial differentials as well. All right. Now that requires more changes, and I don't have time in this video to go through them. But partial differentials, this works as well. Another thing is that infinite series, where you have a plus a1 plus a2 plus a3 on forever. Infinite series oftentimes led to a lot of interesting contradictions, and one of the most famous one that's kind of representative of most of them is known as the Riemann rearrangement theorem. And it says if I have a conditionally divergent series, infinite series, I can rearrange that to basically generate any real number I want. And so it basically says, well, if you're dealing with a divergent series, you're probably going to deal in a lot of contradictions. But if you use the hyperreal number system, you actually eliminate most of those contradictions, maybe all of those contradictions. The hyperreal numbers allow for the manipulation and value assignment for divergent series. And as I said, it simplifies thinking in many fields and proofs. So if this was interesting, some further reading for you. Here's the original paper, extending the algebraic manipulability of differentials. What's funny is, this was done with a co-author, and what's funny is that his uncle actually had his own breakthrough in calculus that was largely ignored, and it's known as visual calculus. If you want to take a look at it, and that's why. I actually got with him on Upwork because I wanted someone to help me either prove that I was right or I was wrong, and so he helped me out and we did this paper together. And so he said the reason why he gave me the chance to do it is because his uncle had a similar experience in this. And visual calculus is actually really interesting, but I don't have time to deal with it here. Another good paper is a student of mine did a follow-up paper called Total and Partial Differentials as Algebraically Manipulable Entities. This paper extends what you've seen here to partial differentials. Partial differentials have their own sets of problems, but again, it solved by taking the concept of infinitesimal seriously and taking a second look at the notation. I also wrote, it's kind of a white paper, Simplifying and Refactoring Introductory Calculus. And this is, so I have a book called Calculus from the Ground Up, and which basically does calculus based on taking infinitesimals seriously. And this kind of is describes why that's an easier approach, why you get more done with less. And basically what I've found is that students actually, by the end of it, have a very solid grasp of calculus with quite a bit of ease. Simplifying and refactoring introductory calculus kind of walks through the way that I teach calculus and why I think it's a really good method. And then finally, just for something a little bit different, but dealing with the hyperreals, this is a paper I did with several others, Logan Gastra and David Namati. This is hyperreal numbers for infinite divergent series. And it's basically showing that with the hyperreal number system, you can deal with divergent series in a rigorous, consistent way. And then finally, I want to point out what might be the guy who made this all possible is Dr. Robert Herman. He wrote a book called Non-Standard Analysis, A Simplified Approach, and most of the people that I know who first got into the hyperreal number system, including myself, started by reading Herman's book, or one of Herman's works about the hyperreal numbers, and he's done a whole lot to champion hyperreals and really move this field forward. So anyway, hopefully that gives you an explanation of what the paper is, what we're doing, and what makes it interesting, and kind of the history of mathematics before and the future of mathematics after, and where this all fits in. So thanks for watching, and I hope you take a look at how hyperreal numbers might benefit you.